Have you ever just looked up into that huge dark night sky and felt a sense of awe at all those little points of light staring back? For as long as we've been human, we've all asked the same question: what makes stars shine so bright? Well, the answer isn't calm or gentle, not even close. In fact, every single star you see is a colossal nuclear reactor, a place of almost unimaginable violence and power. So today, we're going on a trip to the heart of one of these celestial furnaces to see the process that's been lighting up our universe for billions of years. Our story starts in the cold and the dark. Scattered across the universe are these immense, swirling clouds of gas and dust, many light years wide. We call them nebulae, and they're mostly made of hydrogen, the simplest and most plentiful stuff in the cosmos. For millions of years, these clouds just float. But gravity, the universe's silent architect, never sleeps. Slowly, patiently, it starts pulling these clouds of gas and dust together. Think of a snowball rolling down a hill, getting bigger and bigger. As tiny clumps of matter attract more matter, their gravitational pull gets stronger, and a cosmic feedback loop kicks in. The cloud begins to shrink, pulling more and more material toward a single, ever-denser core. As all this gas gets squeezed together, something important starts to happen. The pressure goes through the roof, and the cloud begins to heat up. It's like when you pump air into a bike tire, and the pump gets hot from the compressed air. Now, just imagine that on a scale involving quintillions of tons of hydrogen gas. This dense, hot, glowing ball of collapsing gas isn't quite a star yet. It's a protostar, a star in the making. And sure, it's glowing, but only because it's incredibly hot, like a red-hot piece of iron. To become a real star, a true beacon in the cosmos, it needs to cross one more critical threshold. Inside the core of that protostar, the pressure from gravity is almost impossible to wrap your head around. The temperature skyrockets into the millions of degrees. The hydrogen atoms are stripped of their electrons, creating a superheated soup of charged particles we call a plasma. In this soup, protons, the nuclei of hydrogen atoms, are zipping around at insane speeds. Now, protons all have a positive charge. And just like trying to force the north poles of two strong magnets together, they desperately want to repel each other. Under normal conditions, they'd never get close enough to touch, ever. But in the core of a protostar, gravity is the ultimate enforcer. The pressure is so extreme and the temperature so high that it shoves these protons closer and closer together until they just can't fight it anymore. And when they finally get close enough, another fundamental force of nature takes over: the strong nuclear force. This force is unbelievably powerful, but it only works over tiny distances. It grabs hold of the protons and slams them together. That moment, the instant hydrogen starts fusing, is the moment a star is truly born. This process is called nuclear fusion, and it's the engine that powers every star in the sky. For stars like our sun, the most common recipe is called the proton-proton chain. It happens in a few steps. First, two protons fuse together. One of them cleverly turns into a neutron, and together they form a new nucleus called deuterium. This little fusion releases a burst of energy. Next, that deuterium nucleus collides and fuses with another proton. This creates a light form of helium, called helium-3, and releases even more energy as a powerful gamma-ray photon. Finally, two of these helium-3 nuclei run into each other and fuse. They reshuffle to form one stable, heavy helium-4 nucleus, the same stuff we put in party balloons, and kick out two spare protons. And those two protons are now free to start the whole process all over again. But here's the real secret to why stars shine so brightly. If you were to weigh the final helium-4 nucleus and compare it to the weight of the four original protons that made it, you'd find that the helium is a little bit lighter. About 0.7% of the original mass has just vanished. So where did it go? It was converted directly into energy, thanks to Albert Einstein's powerhouse equation, E equals mc squared. In that famous formula, E is energy, M is that tiny bit of lost mass, and c is the speed of light squared. Since the speed of light is a mind-bogglingly huge number, and you're squaring it, even a tiny scrap of mass gets converted into a spectacular amount of energy. Every single second, the sun's core fuses about 620 million metric tons of hydrogen into 616 million metric tons of helium. That missing 4 million tons of mass is what becomes pure energy, the light and heat that powers our entire solar system. That is what makes stars shine. They are relentlessly turning matter into light.
With all this explosive energy bursting from the core, you'd think a star would just blow itself to pieces. So why doesn't it? The answer is a perfect, cosmic tug-of-war known as hydrostatic equilibrium. Imagine two colossal forces in a constant struggle. Pushing inward is the crushing force of the star's own gravity, trying to collapse it into a tiny point. Pushing outward is the immense pressure from the heat and radiation of nuclear fusion in the core. For most of a star's life, these two forces are perfectly balanced. Gravity pulls in, fusion pushes out. This equilibrium is what keeps a star stable for billions of years, shining steadily. It's a brilliant, self-regulating dance. If fusion slows down, gravity starts to win, which compresses and heats the core, which then ramps fusion back up. If fusion gets too fast, the outward pressure expands the core, cooling it down and slowing the reaction. It's this elegant balance that has kept our sun a reliable source of energy for over 4 billion years. It's this incredible process happening in the heart of every single star that lights up our universe. And this is just one of the countless mysteries out there. If you want to keep exploring the cosmos with us, take a moment to subscribe. We have so much more to discover together. Here's a wild thought. The light from fusion isn't born at the star's surface. It starts as a high-energy gamma-ray photon deep inside the incredibly dense core, and its journey to escape is anything but a straight line. The core of a star is so packed that a photon of light can't travel more than a fraction of a millimeter before it slams into a particle. It gets absorbed, then shot out again in a completely random direction. It might go sideways or even backward toward the core. It's called a random walk, and it's basically a cosmic pinball machine. That one photon stumbles through the star's interior, bouncing from particle to particle for an astonishingly long time. For a star like our sun, it's estimated that it takes a photon anywhere from 10,000 to over 100,000 years to finally make its way to the surface. Think about that. The sunlight that warmed your face today might have been created in the sun's core back when mammoths still roamed the earth. After that epic, rambling journey, the photon finally breaks free. It then streams out into space, taking just 8 minutes to cross 93 million miles and finally reach us. When you look up at night, some stars are dazzling and others are just faint specks. That's not just because they're at different distances. The stars themselves have different levels of power. Astronomers have two ways of talking about brightness: apparent brightness and luminosity. Apparent brightness is simple. It's just how bright a star looks to us here on Earth. A dim, dinky star that's very close by could easily outshine a super powerful star that's very far away. Luminosity, on the other hand, is a star's true, innate brightness, the total energy it's kicking out every second. If you could magically line up all the stars at the exact same distance, their luminosity would tell you which one is the real powerhouse. So what decides a star's luminosity? The single biggest factor is mass. The more massive a star, the stronger its gravity, which means way higher pressure and temperature in the core. This superheats the furnace and sends the rate of nuclear fusion into overdrive. A star just 10 times more massive than our sun can be thousands of times more luminous. These massive stars burn through their fuel at a furious pace, shining brilliantly, but living much shorter lives. One last question people always ask about shining stars: why do they twinkle? A lot of people think the star itself is flickering, but the twinkling has nothing to do with the star and everything to do with us. The light from a star travels for hundreds or thousands of years in a perfectly straight line through the vacuum of space.
But in the final split second of its journey, it hits Earth's atmosphere. Our atmosphere is a turbulent, swirling blanket of air with different temperatures and densities. As that pinpoint of starlight passes through these pockets of air, it gets bent or refracted over and over again. It's this constant, rapid bending of the light's path that makes the star look like it's shimmering and twinkling. Astronauts in orbit see no twinkling at all, just steady, unwavering points of light. From a vast, cold cloud of gas to a raging nuclear furnace, the story of a star is a story of gravity and light. They shine because deep in their cores, they are constantly destroying a tiny bit of matter to create incredible amounts of energy. This energy, born from fusion, pushes out against the crushing weight of gravity in a perfect life-giving dance. The light that's created takes millennia just to escape its own star, then journeys across the unfathomable distances of space to reach our eyes. The starlight we see tonight is ancient history, a postcard from the distant past. And maybe the most profound part of it all is that the fusion inside stars is what created the heavier elements in the universe. The carbon in your cells, the oxygen you're breathing, the iron in your blood, all of it was forged in the heart of a star that lived and died long ago. So the next time you look up at the night sky, remember what you're really seeing. You aren't just looking at distant lights, you're looking at the cosmic engines that built our world and built us. We are, in the most literal sense, made of stardust, looking back at our own origins.